Hello everyone, welcome to today's webinar. I'm Catherine Dold with CNEN and I'll be moderating today's event. This webinar is titled Computational Solutions of Thermodynamics and Rheological Property Estimation of Soft Materials and is being sponsored by Siemens Digital Industries Software. CNEN works with sponsors to identify topics of interest and value to CNEN's audience and consistent with their mission to provide news and analysis of the chemistry enterprise in a timely, accurate, and balanced fashion. During the webinar, you can adjust the size of the slides on your screen by grabbing the lower right corner with your mouse. If you need technical assistance, please look for the Help widget at the bottom of the screen or type your query into the Q&A box. If you get disconnected during the webcast, please log back in according to the instructions you received earlier. You're encouraged to contribute to the success of this webinar by asking questions at any time during the presentation through the Q&A box on your screen. Our speaker will answer them at the end of the presentation, and as your moderator, I'll be posing as many as time permits. Please note that CNEN does not endorse any company, products, or services that may be mentioned in the webinar, and that each webinar will be archived at CNEN Online after the live webcast. Our presentation today is being sponsored by Siemens Digital Industries Software. Siemens is a technology company centered on industry, infrastructure, and transportation. No other tech company is better equipped to combine technologies from the digital and physical worlds to empower customers to reshape industrial and infrastructure systems, making them smarter, more productive, more efficient, and more sustainable. Siemens, part of the Siemens Accelerator portfolio, includes computational chemistry solutions that bring a deep knowledge of quantum mechanics and molecular dynamics, providing multi-scale simulation for discovering innovative soft materials. Our speaker today is Dr. Hans Freye, Science Advisor, Siemens Digital Industries Software. Dr. Freye is a longtime professor, entrepreneur, and algorithm inventor in industrial computational chemistry. He started his career in 1987 as a postdoc in the soft materials laboratory of Nobel laureate Pierre-Gilles Dejean in Paris, then moved to industry where he invented an algorithm for polymer blends formation, and finally to university. He has been a full professor at Leiden University since 1999. In 2004, he started Culgi, a multi-scale computational chemistry company. And in November 2020, Siemens acquired Culgi, and the software is now part of the Simcenter suite of solutions. Professor Freye is currently an advisor within the Digital Industry Software division of Siemens. Throughout his career, he has actively participated in more than 50 industrial projects and numerous EU research grants. I'll now hand the program over to our speaker.
Okay, thank you very much. I hope everyone can hear me. My name is Hans Freye, and I will be talking about computational solutions of thermodynamics and rheological property estimation of soft materials. That is what I will do, but you will remember one thing after this presentation. I will be talking a lot about the so-called value chain. This brings me to the answer to the very important question, why would Siemens be interested in going into computational chemistry? Well, the answer is simple. When we look at process industries, chemicals, personal care, pharma, there is a value chain all the way from early stage discovery to engineering, to manufacturing, to finally logistics and going on the market. In all of that value chain, there are bottlenecks. And one of the bottlenecks that we will be talking about is the bottleneck from early stage discovery into engineering. And Siemens is very interested in providing solutions along all of that value chains, which includes also then discovery, computational chemistry. Okay, so remember that, the value chain. So why would materials discovery be important? Well, we believe that it is actually critical in the 21st century, and this is because of sustainability. We want to go away from petrochemicals and maybe want to use bio-derived chemicals, which is an issue by itself because bio-derived chemicals have a very different nature than the simple oils we used in the past for petrochemicals. We want to make smart materials. We can think of batteries as a very smart material. We can also think of self-healing coatings as a very smart material. We can think of liposomes, so drug delivery systems, of course, is very smart materials, as we all know, in the times of COVID. There is ensuring intellectual property protection. The competition in the market is increasing at a phenomenal rate because of the rise of companies in Asia. And on top of that, we have to provide evidence of performance, and which means that customers, be it business to business or business consumer, are increasingly aware of what's going on, and they're very, very vocal. And so the time is pressing, and we need to come up with a way to increase the value chain, or the speed of the value chain. So look at this picture here from, let's say, one can look at this picture from two different points of view. If we say we want to increase the speed at which new materials are brought to the market, then one can think like, let's say, standard or a traditional computational chemist, maybe a student or a professor at university. Let's make molecular dynamics 10 times faster, which is very valid, not bad at all. But you can also look at the other point of view, maybe more like a CEO of a company or a CTO of a company, and that the person would say, I have a value chain all the way from the discovery to the market. So where are the bottlenecks in that value chain? There is a bottleneck from product design to materials research. I will not talk about that. There's also a bottleneck when you go back from manufacturing all the way back to product design. There's one other bottleneck that I will be talking about at length today, and that is once you are in discovery, in materials research, how then to make it such that you can speed up going into the next phase, that of engineering. And so, as I said just before, the demands are incredible. We want materials to be more powerful, but we want them greener. We want materials to be lighter, but also stronger, and so forth, and so forth. So a lot of these, let's say, demands are conflicting. So there is a stress on this materials research, on the whole value chain. So we have a tale of good. There are more barriers in this whole value chain, but many of I will not talk about all of them. I will just talk about the gap between chemistry and engineering. So in chemistry, one can think by having questions like which ingredient has what function, what intermediate step is necessary to reach a final product, and so forth, and so forth. In engineering, one has other questions. So in process development, what sequence of steps will be followed? What are the intermediate chemicals and solvents needed? Very important for process engineering. And so one can also go into scale up. What scale up rules to follow? Are the intermediate ingredients, solvents, environment friendly, and so forth, and so forth. And of course, will you make money and deliver on time? Now, there are two gaps here. That is maybe not very familiar for the chemist, but in engineering, this is very well known. There is a considerable gap between the process development and the engineering scale up. And within Siemens, this has been recognized already some time ago, and there are lots of methods within the portfolio of Siemens Simcenter to deal with that issue. I will not talk about them today. I will just briefly mention here computational fluid dynamics, that is the CFD. We will be talking about that quite a bit. So we were talking here about the first gap, that is the gap between chemistry and engineering. And so this is, let's say, in a nutshell, what this is all about. This is a picture from a typical way that nowadays in laboratories, in many chemical companies, pharmaceutical companies, personal care companies around the world, new materials are being developed. That is, in the center of the whole setup is a robot, and the robot does many experiments. Let's say maybe 1,000 a day or something like that. And usually that robot is surrounded by maybe 10 people. Now that robot is fed in by a person coming up with an idea, let's say the product design, that can be based on all kinds of input from the market. We will not talk about that. That's a very difficult step, by the way. That's for a different seminar altogether. Then there is computation going on. Can be with molecular modeling, can be AI, something like that, design of experiments. But if you look at this whole picture here, there is actually a very slow step. And the slowest step in all of this is not a robot, but that is the step going into engineering. So in a typical company, and we know of some of these personal care companies that do maybe 40,000 formulations a year, that is actually more than 100 a day. And this is, let's say, for one robot, there's a lot of information. And but if you do scale up, if you want to then to make your shampoo or whatever you have in a big vessel and make maybe 1,000 tons of that in a year, well, then you hit the bottleneck because you're not going to do 40,000 scale-up experiments in a year. Maybe 10, maybe 20, maybe 100. But that is way not as much as what you do in screening. So screening is fast, 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 and the scaling up is slow, slow, slow. So that is a real bottleneck. And on top of that, to increase the challenge here, is that nowadays one can think of, okay, you generate a lot of data, let's turn on an AI. Okay, very popular, but you have to be very careful with that because we talked just about sustainability, batteries, smart materials. A lot of this chemistry is new, which means that you don't have data from the past to calibrate something like an AI. On top of that, in these formulations, the chemical space is enormous. One not only has concentrations and chemical groups, but any combination of that, which means that, for example, for the liposome from Pfizer and Moderna, one has millions and millions and millions of possibilities. And the fact that we have that liposome working is almost pure luck, I would say. So this is more than atoms in the universe. And so this is one message here, be careful with AI. Let's go to the next slide. And this is why we then would want to go to physics-based modeling. Well, I just mentioned that even although you generate a lot of data in the early stage discovery, that data is still limited compared to what you need for a full-blown AI. There are other areas where this is different, for example, in protein structure prediction. We will come to that in a moment. But in this formulation, so the possibilities are endless. So we need to, if you then want to do computational materials discovery, what you then want to do is this. You want to be able to screen your new materials at the pace of the robots that you have in your laboratory, similar to what happens in a pharmaceutical design. You need to include thermodynamics because you want to include in your screening a possibility to say if your product or your process is stable, or if your product is stable to survive the process. You also need really to include rheology because one of the most important aspects in scaling up of these complex formulations is, what is the rheology of that? What is the viscoelastic behavior? This is something that will come back also a few times. Viscoelasticity is way more complex than thermodynamics, and the more insight you can get into that in an early stage, the better it is. To speed up the whole value chain, remember that. And to make it even more challenging, that in many modern formulations, I mean, maybe not in the batteries or the liposomes, but in many polymer-based materials, one includes reactions and phase behavior simply because that is a lot more less expensive than doing it in the other way. And doing experimental screening with robots with reactive formulation is extremely difficult / impossible. So the short message is, if you want to speed up the value chain for these complex materials, you may want to use AI, but you better use also physics-based, coarse-grained, and mesoscale models. Okay, so the vision that we have is integration and digitalization. And as I said, what we need is really a handshake or a marriage between chemistry and engineering. So the engineer should be able to say back, can we use here the material composition as design variable in the process? For example, what happens if you change the solvent? Would it affect the material, or how would it affect the process? That is a chemistry question. On the other hand, we have the chemist, and if the chemist can include the engineering properties in discovery mode, as we will see, that would be a great aid in speeding up the value chain. So you need a handshake between the two. Now the solution is, as we would say, unity in diversity. There are within Siemens many, many different software tools available for lots of stuff. And this is all about unity in diversity. How you can get them to work together. There's a very important social and cultural and historical element to that, right? I am from Leiden University, classical university, chemistry. Nearby is Delft University, technical university, that's engineering. And it has been always like east is east and west is west. This is fine, and we can survive like that, but not in the 21st century with all the challenges that we have. So we need to figure out how to cross this value. I'm not going to talk about all the social aspects of this. I'm going to talk about the one aspect that we can solve with the current tools, and that is algorithms. This value translates into, on an algorithmic point of view, into, for many materials, into the valley that exists between left-hand chemistry scales, that is quantum, molecular coarse-grained, that is discovery, to the right-hand scales of the continuum mechanics and even the scale of equipment going on to the length scales of the entire plant. So on the right-hand side, continuum equipment plant, that is the standard of the classical Siemens territory, right? This is process models and engineering. Excellent, they can work together. They have been used many different applications. Very useful. On the left-hand side, we have a whole range of methods that take information all the way from the quantum to the mesoscale that acts then as a bridge in crossing over to the computational fluid dynamics. It is not always necessary to really go into a mesoscale simulation to cross over to engineering. There are also a lot of examples where you can take, for example, a quantum-derived structure and put it into a thermodynamics that goes into distillation columns. So that's from the right to left. We have examples of that too in a moment. But overall, certainly for structured materials, we need to go all the way from quantum to meso, and then to the continuum, etc. So that was the grand vision. Let's now go through the reality of algorithms and how it works in practice. So here again, a short overview of the typical questions we get when we talk with questions. A very important question that we many times get: can you now predict the shelf life of this material? Or was it a phase diagram? Or can you now predict the viscoelasticity and stuff like that? Okay, I guess that most of you will understand or know about these questions. So what properties can we now estimate with Simcenter Culgi, given the context that we work in? So we were talking about constitutive equation formulations with a novel algorithm. We're talking quite at length about that one. Then I will also talk about partition coefficients. For example, the partition coefficient that you need to predict if a packaging material is good for you or not. We will also talk about solubility coefficients or similar methods, and we will talk about permeability of membranes. It says here polymer membranes, but the picture is, you will recognize this, lipid membranes. Okay, we have three classes of properties that we'll be talking about: thermodynamic properties, VBA properties, rheological properties. Let's skip that very fast and go to the first topic, that is partition coefficients, permeation coefficients, stress-strain relationships, and phase behavior. And on all of that, partition coefficients first. So we use here, partition coefficients are what finds them many, all over the place. You have a mixture of something, and you have an active ingredient of something, and the partitions in your process or in your final product in between phases, and what is the fate of that? Can you predict that? Now here, one needs to recognize here that the world is changing very fast because of the same sustainability. We go away from petrochemicals. In the old days, not so long ago, this question maybe could be answered by some kind of QSAR based on petrochemicals. And there's lots of data available in various databases to calibrate such a QSAR. Maybe you would call that now AI. But this is not what the future is telling us. The future is telling us that we want to use much more complex molecules, large molecules, molecules that are almost like nanomachines that can do some clever stuff. And if you want to predict the fate of those molecules, you really need to go to the quantum description of those molecules. You can no longer use groups methods or descriptors that you would do in AI. It's impossible. You don't have enough data to calibrate that. The only method that we could figure out that would be useful for that, or could be used for that, is a method derived by a good friend of mine, of Andreas Klamt, COSMO-RS, that takes the charge density distribution of a molecule and then combines it with some clever thermodynamics to predict a partition coefficient or a GX in mixing. It's a good method. It's very fine. It's one of the best methods available in the future, but in the world. But this method relies, certainly in concept, on quantum calculations, DFT, density functional theory calculations, which are very expensive. And in screening, you don't have that capability because, expensive meaning takes a lot of time. We want to do the screening, and so we want to do something in a core minute. So what you do then is we recalibrated semi-empirical quantum method AM1. We call that ABC. This is a lot of correction there. And with this ABC method, we can now suddenly calculate the partition coefficients of even large molecules in just like a few minutes. And this means any type of molecule. So it's no limitation groups or whatever. The same as in any quantum method. So on the left, this is published work. If you want to see that in more detail, you can do that. You can look it up. This is partition coefficients taken from the BioBy database, large collection of that sort that we know of, and we got actually a very good result. And then we tested the calculation method on calculated or measured partition coefficients of very large drugs going into the sample 5. That's a challenge, and the experimental value is on the horizontal, and the vertical is on and is the calculated one. And actually, we beat all the competition, and we also beat Klumt himself, which is something. But Klumt himself also beat all the other competition, which is also force field methods, engineering thermodynamic methods, and so forth and so forth. So we have a method here which is faster and actually more accurate and can be applied to any type of molecule. And the method is also not limited to hydrocarbons at all. Because of the nature of the quantum calculation, you can actually use it for any type of solvent. So let's see an application of this immediately, because partition coefficient between hydrocarbons and water is maybe not that, it's nice, but okay, what do you do with that? Where this method comes immediately into place is in membrane permeation coefficients predictions. This is again a very important topic. I will talk about it in a moment, but first I will talk about the coarse graining nature. So this is what you do when you have an inhomogeneous phase. What you just talked about, partition coefficients, is between solvents. These are homogeneous. So you can then do a quantum calculation and you have your solvent and you can do equation-based thermodynamics. Very nice. But now we go to structured phases, as you would have in the batteries, as you would have in the liposomes, etc., or membranes. And then you have things in 3D, and you can no longer do this homogeneous trick. You really need to represent the 3D. And since we are aiming for a screening speed, right? Remember that. So a few minutes or hours per system at most, then you need to coarse grain the molecule. There's no other way around that. But the coarse graining needs to be done with two constraints. First of all, you need to be able to represent any type of molecule by a coarse graining procedure in an automated way, because we want to do everything automated by a theory. And the second is it has to be thermodynamic accurate. And so we do a trick. So we say, well, the structural information comes from the bottom up, so that's from left to right, and we will use ABC to get the quantum envelope. But the thermodynamics we do from the right to the left. So we take from engineering thermodynamics, we apply that to the beads or blobs or whatever you want to call them, coarse grain units in your molecule. And all of this is automated, also being published. So an application of that is what you see here. This is permeation of large drugs to lipid membrane, a very important topic. Because many modern antibiotics are based on cyclic peptides. Cyclic peptides are very big, or maybe you have protein inhibitors, also very big. These are molecules, drugs that are easily in size of molecular weight 1500. And it turns out, so we have done the coarse grain simulation and all of that, including then the ABC method and the partitioning coefficient, etc. But you see here in the graph is on the left-hand side, you can maybe not see it very well, but that's the volume of the molecule. On the left-hand side, top center, these are, let's say, the old drugs, like the drugs as we used to have in the 80s and the 90s. But on the right-hand side, we have the drugs that we are now developing, which are much, much bigger. And here there is a bit of theory, that's a red line. That is me, professor speaking, theory here. The red points are from coarse grain simulations, and the black points are from experiments from the Locky group. This is, I believe, the first time and that someone has been able to mimic this by simulation or theory. And this goes all the way up to molecular weight of 1500. And as I said before, these calculations maybe take a few minutes per molecule. And the effect of the size is enormous. You see here it goes from 0 to -4 on a log 10 scale. So this is 10,000 times slower to permeate than that guy over there. Let's go to, again, a different application. So we will talk a little bit between application of pharma and materials. I hope you will appreciate that. This is also a very important, very timely topic. We all know about AlphaFold that is used to generate structure from our friends from DeepMind. A very impressive piece of work using AI based on all the structural databases that we have for proteins to come up with a structure. Those structures are not maybe good enough yet to do a small drug discovery, but it's more than good enough, as we have discovered, to connect with coarse graining and to say something about the formulations or the aggregation behavior of those molecules. So what you see here is one example that we have been working on, and since AlphaFold was published just a couple of months ago, you understand what enormous amount of work my team has done to make this work in a very short time. But because with automation, we were able to do that. So we take the structure from AlphaFold generated as is, then we feed it into Simcenter Culgi. We do our automated coarse graining technology, maintaining the protein systemic profile. We come up with a coarse grain structure, and we dump that as is without any further adjustment in a coarse grain simulation environment. This is, I believe, DPD. We will also talk about another simulation method at the moment. And then we calculate actually the aggregation of the molecules in water. And then what we see is in a small concentration, low concentration, there's no aggregation, and 100 nanometer is actually concentration. And this is a protein for which until a few months, well, nothing was known. And so out of the box, we predict here the aggregation behavior of a molecule, which is very important for a very, for a disease like multiple sclerosis. So I think this is amazing. I did myself not do the work. This is a person working in my team, Panos, Peters Panos, but it's really, it has a lot of future. So we also now apply that to antibodies and to vaccination and so forth. Let's go again to a different application. This is food packaging. We have here, also shows here the relevance of these methods for a very important topic in food packaging. This is from SABIC. Food packaging is a very nice example of a very smart material, although maybe it doesn't look like a very smart material, but it is. One has multi-layer plastics packaging, one has adhesives there, and the short story is you don't want the plastics or the ingredients in the plastic, so actives that you have added there to poison your food, and you don't want the food leak out into the environment, and you don't want oxygen in, and at the third time you have to be transparent so you can see inside, and you may want it really to be sustainable, and you don't want, and you want to biodegradable, and so forth and so forth and so forth. So it's enormous difficult to do that really, and so what we did here is come up with a good plan to predict the fate of small molecules as it would permeate through the packaging. Very complex material, very smart. Then another thing is this application of this automation. So why would we do that? Well, you can also not do that, and if you have plenty of time and you want to have all your molecules in your system to coarse grain, maybe you have enough time and you can do that. So there's of course a lot of work, especially in academia, to do that. But in industry, this is impossible. So this is a good example why this is impossible. This is an application of AFP to enhanced oil recovery. This is something that we did with Petronas. Again, by itself an interesting story to tell here, of which I didn't have time really. But the short story is that they have lots of oil still in the rock deep down beneath the sea, and they want to use surfactants to get more oil out. That's the short story. And so they used actually Culgi to predict what surfactants would be best, or what surfactants mix would be best to that. And Petronas actually represented the crude oil by AFP in, I believe, 100 different components or something like that. And all of that was done in an automated way. So there's no way they could have done this with a manual method. You really need automation here. And this ABC stuff and so forth. Now let's go to the last topic. And all the topics that we have talked about are important, but this one is, I like myself because it's very interesting. So this is a stress-strain relationship, and we will go to rheology. So remember that we talked in the beginning and say we want to go into engineering, and one of the important aspects in discovery is how to get rheology in there. How do you do your robotic screening by also measuring something that you can get out of that for rheology, and especially you want to do this for these very complex reactive systems. So why would we need, or why is it that we would want to do that? I remember, so we are Culgi's part of Siemens, so within Siemens there's an enormous community of computational fluid dynamics, CCM+, has been around for some time. And so this kind of thing has been there for some time, and I'm going completely away from force fields and quantum. I'm going to constitutive equations, the world of constitutive equation. I'm going from particles, I'm going from continuum, or at least that is what the CFD would like to do. They would like to do that. But the reality is when we do molecular modeling, we have particles. And we have force fields. So how do we bring that from that world, also, let's say, an understanding, a very important aspect of that, a social, cultural aspect of that, remember that I said that, to the world of, well, the engineers to do CFD. Well, this is one thing. So the challenge is that many polymer materials, maybe unexpected for my friends from academia, are made in a reactive way. So this is not only polyurethanes, polyamides, but many, many more, or are performing in a reactive way, adhesives, glues, coatings, and so forth. So how to come up with a constitutive equation for that? The existing system specific, the existing constitutive equations actually are only so-so, and actually do not contain really good methods to get molecules in there. So what we would say is we would do a Culgi simulation on a coarse grain level to develop system-specific constitutive equations. Let's say throwaway constitutive equations. So, you know, only for that system, not generic like reptation or something like that, or the pom-pom model or something like, or the Pantene Tanner model or something like that. Okay, these are all generic fixed constitutive equations. We want to make it system-specific. And as much as possible, we want this to be based on a recipe, including the effects of fillets, whatever, fibers, fillets, etc. So, and what would be the benefit for any company is to reduce the cost of developing a parameterized constitutive equation. So, you know, if you think about these formulations and they come out of the laboratory and then you want to scale them up, if they are very complex viscoelastic behaviors, maybe there is a phenomenological constitutive equation that you can use. These equations that you would be able to use for that, like the PTT model that I just mentioned, they will easily take tens of parameters. And the time you will need to parameterize those equations is really months. So this is the reason why this scaling up is so difficult and so time consuming. So we need to get a lot of that back in the discovery by a digital means, by a model. This is a bit of a funny slide, perhaps. So the first case that we will discuss is polyaramide, also known as Kevlar in the United States. In Europe, or we would say maybe more Twaron. But the short story is this. We start all the way on the left here with the monomers, aramide solution, aramides, monomers. Then, you know, you scale them up, you make a coarse grain model of that, and you do some shearing, and then it goes into the fiber. And the fiber goes into a kneecap, like what you see here, and the kneecap is used in protective clothing. But this kind of stuff is used worldwide in many, many different applications. And then finally, you can use it for attaching a roof. Actually, this is my own roof here, my own house here in the Netherlands. Very nice work, I must say. So there are also a lot of stories to tell about that. I don't have time for that, but if you want to attach your own roof, you can contact me. Then we have here quantum-derived structures. So how do we do that? So we take what we just said. We start with this ABC method to coarse grain or to get the quantum envelope of these monomers. This is here an oligomer. And then we use the AFP method to set the coarse graining of the polyaramide. We take here rough setting. AFP by itself has a scoring function where you can set in many, many different ways, like meta parameters. So how many heavy atoms do you want per bead, or maybe you want to maintain rings or not. So there are many aspects of that, or what the volume or something is, or the surface. There are many aspects you can set at the scoring function. It's like simulated annealing. We have taken here a very simple one at setting. Okay, we will do 6 atoms per bead. Again, all of this automatic. And then we go into rheology, microrheology. So we put the whole thing, the monomers, into a small simulation box, and we turn on coarse grain simulations. And now we use a method called Stokesian particle dynamics. This is not DPD, dissipated particle dynamics. It is also not molecular dynamics. It is also not Lattice-Boltzmann or smoothed particle hydrodynamics. It is something new. It is called Stokesian particle dynamics. In short, what SPD does, it takes the same principles as DPD, but with one very important change. We have removed all inertia. And why did we remove all inertia? Because in this domain of submicron flow, that is creeping flow, which means no inertia. This is, again, when you step over to computational fluid dynamics, you will understand this immediately. Now this is SPD dynamical method has been, we have modified it again a little bit with, and added also kinetic Monte Carlo, which means that we now can do coarse-grained reactions. The calculation, what you are going to see, take 2 core days, so that's still on the level of screening. If you have enough cores to you available, you can try many different recipes. Maybe not core minutes, but core days, I think for such a complex problem is already very fine. And then what the fun thing starts when we realize that because we can measure stress and velocity, we can actually calculate the constitutive equation from a single simulation. So for a simple liquid, the constitutive equation is simply, Newtonian, this viscosity here. And for these materials that we have, of course, it's not true. So here, the x-axis, we forgot to put this in on the picture here. The x-axis is in that direction. So what you see here, x is in that direction, and what we do while the reaction is going on, you will see this in the next slide on the video. While the reaction is going on, there is a body force like this, like a sinus, which pushes the liquid in that direction here, and here in that direction. And while this is going on, the reaction is going on, the conversion is going on, and we measure instantaneously the stress profile in that direction and the velocity profile. This is more or less at the end, so conversion 95, 96% is what you can get with polycondensation. And what you see immediately, for example, here in this region, the velocity profile is very flat here, right? Very flat means a low gradient, means a very high viscosity because the stress is not zero. Here, you have a simple gradient here, linear slope almost, and then you count it back, and then you have a lower viscosity here. So in principle, from this simulation, one can calculate the viscoelastic response as a function of conversion in one shot. So let's look at the let the video as it plays. So we have the conversion going on here. So that's increasing, longer and longer polymers are formed by the polycondensation, and the developing stress profile is in this direction, as I said. Initially it was really sinusoidal. That went very fast, but already after maybe 40–50% conversion, it started to become this much more flattened envelope here. And at the end, after 90% conversion, you will see you have very long polymers. And as in polycondensation, this is very heterodispersed. You see here these long polymers, but you also have much smaller polymers. And what you have also seen, that it is like you have here extreme shear thinning, and in the middle it develops almost like a plug flow. So you have thixotropy, you have shear thinning, you have the whole rheological spectrum, from any textbook you have in one simulation. And it's really amazing. Okay, we will come back to that in a moment. Let's go to polyurethanes per. So if you want to make polyurethane, you need at least 2 polymers. This is additives. There's a very wide selection of chemicals. The isocyanates and polyols, each of them you can select from hundreds and hundreds of different chemicals the industry provides, and this leads to an extremely wide variety of materials properties. And you can almost see it like using amino acids for making proteins. So very broad applications. So 3 applications stand out. We have been talking a lot about business to business, so what happens in the industry, right? In the process, in the value chain, but there's another application that is, suppose you do reactions in-house, so as a consumer, and this is what you do if you yourself make a coating out of PUR. You can buy that stuff, and then you make your own coating out of PUR, and very strong, very stiff, but these have very rheological properties because you don't want the stuff to form a hard coating while it is still flowing. So also here you have lots of, let's say, competing demands. Other application, reactive injection molding, where there is basically nothing in COD at this moment that can say something reasonable about that. And there's also foams and construction materials by itself, also again a huge area, and I really don't have the time to talk about that. So today we talk about the molecular level all the way to coarse-grained level, and we will do the same as with the Kevlar stuff. So we have the monomers in a simulation. And in this particular example, only two of them, one polyol and one isocyanate. We have some parameters for the kinetic Monte Carlo, and here we go. And then the same as in the Kevlar, we do we calculate the stress and the velocity profiles in the system. And what I just mentioned here, what you saw in the Kevlar, you had these plots of stress and velocity. Well, the two of them, as I said, is what you need to get a constitutive equation. So you can formally define an effective viscosity simply as a ratio of the stress and the velocity gradient. So there's the rate, strain rate here. So that's the gamma point here, which you can actually calculate from the gradient of the velocity profile. So supposing you have measured, you have done an accurate enough calculation and not too much noise, then you can actually do this as a function of conversion. So what you saw in the Kevlar, conversion went on, and we only showed the video, but for each snapshot in that, you would be able to do that. And this is what we have done here in the per case or polyurethane case. So we have now as a function of conversion, look at the blue, here the orange, and then the green, and then the red. And here on the horizontal, we have the log of the shear rate, and here the log of the effective viscosity. And so, and you see here that as a function of time conversion, the viscosity goes actually sky high, which we expect. It is also what happens here because this forms a network that the elasticity also changes a lot. I'm not going to talk about that here today because, again, that would mean a different webinar altogether. But this is very interesting to be able to calculate that too. Okay, now here, this envelope here, this is funny too. This is the envelope which you see is actually the Karu-Yasuda model. And that model is in star CCM+, and is also other CFD packages, I must honestly say. But star CCM+ has that too. So look at here, generalized Newtonian models. We have lots of models there, power law model, cross models. And this is the guy that we need, Karu-Yasuda model. It's an empirical model, completely empirical. There's no molecular or whatever motivation there. It just says, okay, when you have a low shear rate, you have a plateau. When you have a large shear rate, you have a plateau. But that plateau is lower because you have the shear thinning, and let's just draw something in between. Okay, that's basically the Karu-Yasuda model. But you see here, it comes out of a simulation. And the only thing that we need to do to change this or to modify this is to change the recipe of the polyurethane. So suddenly we have a very important link between molecules and, until now, a purely empirical model. And this is, we believe, will certainly speed up the value chain. Which brings me to the last couple of slides. I did not talk about the software too much. I assume most of you will be experts in some way or the other. So you will have seen molecular modeling interfaces we have. We have the same type of interfaces, everyone has, but we have one big difference. That is, since we are focusing on very complex formulations from the start or the inception of Culgi 15 years ago, 16 years, 17 years ago already, I made a very conscious decision that instead of focusing on a graphical interface where you would, the typical, say molecular modeling interface where you would design, we have that too, of course, like everyone has that. But really the workforce of what we do is writing these scripts. And these scripts we write in an intelligent development environment that we created ourselves. But we can also export that to Python. And the Python environment gives us the possibility to connect to all kinds of other software. So we have a very open data structure. For example, connection to AI is now almost trivial. So let's, again here, let's say wrap it up a little bit. So I talked about the quantum in Culgi, so NWChem, but I talked especially about ABC. Of course, we have NWChem2 and similar methods. But I did not talk about molecular dynamics at all. I did talk about mesoscale modeling, but then only about with Stokesian particle dynamics. I did talk about the scale mappers that we have, especially from molecules to coarse grained. We have other scale mappers as well. There's no time to talk about that. I also did not talk about engineering thermodynamics. Briefly, I mentioned CosmoRS. We also have a workflow for UNIVAC that the chemical engineers will recognize UNIVAC. Also, we have an extensive module for chemical informatics and connection to AI. We have also lots of molecular density functional approaches. So there's also Mesodyne here, something I invented more than 30 years ago. There's also risen there in 1D. There's marker structures. There's a very open data structure. So with Culgi, you have complete access to all the parameters of any method that is in the system. We have applications, nanorheometry, solubility. We have lots of examples. And we have a library of molecules that are already cross-mode, so to say, to get you started. The key technology to achieve desired results That is Simcenter Culgi. We have this fantastic intelligent scripting editor that unfortunately I did not have too much time to talk about, but it is really great, I think myself. Then we have this ABC method to calculate Cosmo charge envelope of molecules by bond-corrected semi-empirical quantum calculation, very fast and accurate. We have algorithms to coarse-grain molecules automatically, fast and also accurately. We have the new guy on the mesoscopic dynamics front, that is Taussian particle dynamics. These are algorithms for simulating creeping flow, particle dynamics on a microscopic scale, including reactions. So most of this has been published, except the other one, SPD. If you want to know more about SPD, then please contact Siemens. The summary and outlook here is we have demonstrated 3 novel methods for property estimation, 4 use cases, and we have also talked about why property estimation is a crucial step. And and remember what I said right in the beginning. You can forget all about these algorithms. Maybe I talked too much about them, but remember this one thing: it's the value chain. You need to learn to think value chain. And what are the bottlenecks and how do I reduce them? And this is what we do in Siemens. So the presentation that I just showed you will be made available through CNN. All questions will be forwarded to the presenter. And for sales inquiries, please contact Siemens. This is my presentation.
Thank you for a great presentation. We have a few minutes left for questions. Just a reminder to our audience, you can submit your questions in the Q&A box at the bottom of your screen. And as our speaker just mentioned, any that we don't get to today will be answered by email later on. And so let's get to our first questions here. Let's see. On the mesoscale, sometimes a single parameterization fails to capture various properties. For example, CG models for surfactants and water cannot describe CMC, air-water surface surfactant tension, and oil-water surfactant interfacial tension with all the same parameters. Okay, the question is there a way to automate the formulation design if one needs to consider all 3 properties at once?
Yeah, that's actually a great question. And I myself spent with my team science quite some time on that already a couple of years ago. When we first came up with the idea of AFP, so the automated fragmentation parameterization, this was actually the first thing that we did was not writing down the equations, but to think of what is the data, where is the data, what kind of stuff do we want to simulate. So we want to have the partition right? That is given, but we also want, because we do microstructure things, we also want to get surface tension right. And also we want to get this torque thing that I didn't talk about, but it's like surface tension plus, I would say. That is what you need to get into microemulsions. So we did quite a bit of extensive calibration of this AFP, with all the data that we could lay our hands on. And the beauty of all of this is because this is automatable, right? And the scoring function that I mentioned but did not talk about has meta parameters by itself. Actually, you can do this entirely yourself. So once you have the data on surface tension and partition and phase diagram, so mixing free energy, for example, there's nothing that prevents you to find the meta parameters in the scoring function to find the good way of doing all 3 of them. And even more, also the density. It took some time to work on that. So, and what else? The compressibility, I believe, yeah. So that is the beauty of having these meta parameters on a higher level. So instead of doing this by hand, painstakingly beat for beat, this is what we used to do in the beginning. So 2004 until maybe we came up with this AFP. So that's 10 years ago. Before that, it was really bad. But with this AFP, you have a lot better handle of doing a meta parameterization on everything you can lay your hands on. But you need data, of course, to do that. Metadata. Not your formulation data, but data on partitioning, like the biobate, data on surface tensions between solvents and stuff like that. We can help you with that if you want.
Okay, thank you. Next question. In which of your examples has there been the largest impact from these calculations?
Impact in what sense? The questioner didn't ask that.
Sure. Right? In which of your examples has there been the largest impact?
I would say I would love to say that because of all the scientific innovation that fantastic this and fantastic that, but to be honest, I think the largest impact we had on this company, Petronas, because Petronas was a company that before we came on board did not do any computational chemistry. In fact, what happens in many economies in the developing world, and maybe Southeast Asia is not any more developing world, but anyway, that are developing technology and industry and universities, is actually great to help them in doing something for the first time. So that we worked with them and trained those people and helped them in getting this thing working, that was far the greatest impact. I can say, okay, we did, because of that, we did the surfactants faster, but the impact on the persons in that company, that was, I'm very proud of that.
Thank you.
There's maybe a different answer than you would have expected. Yeah.
Here's an interesting question. What educational level, experience, or prerequisite knowledge is needed to be proficient with using the software?
Oh, that's an excellent question. Now, I have good news and bad news. The good news is that I myself have been using the software in teaching at Leiden University for a number of years, and I teach that using this same software that we use here on the undergraduate level, the third-year undergraduate chemistry. Now it's a bit higher level than you would have in the United States. Maybe in the United States it would be master level, but anyway, those students, they picked up the software in maybe 6 weeks. Starting with nothing, no knowledge of software writing even, but with the help of this integrated development environment, we were able to teach them at the end how to make these lipid membranes that you just saw in the permeation coefficient calculation. Of course, on that level, students will not understand all the different methods, so you have to be careful how you do that, right? So this is teaching, undergraduate teaching. They managed to do that, so I would think everyone, who has a bit of understanding of modeling can do this too. I understand that this can be daunting, that you say, okay, I wear what button to push, and then you see a script editor in front of you. I can understand that. But we have a lot of experience in that, and so we have an extensive training program to help people through that. And our experience, if you are, let's say, an experienced computational chemist or a computational chemist in a company, and maybe you have a background in quantum, or maybe you have a background in molecular dynamics, for such a person, 3 days is more than sufficient to pick up the software. Of course, the science that goes in there, right? I talk very easily about that, like the permeation and the science. Of course, a different matter. The science takes much more time, but that's your own responsibility. You have to see the software as a tool. The software can do great things, but that is your own responsibility.
Okay, thank you. Next question, does it require accurate knowledge of molecular formula and structure? How to use for naturally derived molecules, for example, milk proteins?
That's also a very good question, because a long time ago I did my PhD on proteins. I worked on serum albumin. At that point, the structure of serum albumin was not known. So I would say there are two answers to it. So of course, we discover many applications, certainly in, let's say, formulating with natural ingredients, that one has only a bare understanding of what's the chemistry inside. We understand. And in this case, like we did in a crude oil, that of course has an enormous variety of molecules. In that case, what we would suggest, and what has been very helpful for many companies, is that you use the software, first of all, as a molecular generator. So there's not one molecule in your system that will do the thing, right? It's not like you're talking about a drug molecule. You're talking about maybe if you want to formulate a polysaccharide for a thickener, as a thickener in toothpaste, for example, then you may want to generate with the software, first of all, a bunch of carbohydrates that, to the best of your knowledge, mimic the envelope of structures of molecules that you have in your real system, like we did with Petronas. That is, I think, by far the best solution. To do that, and since we have all this automation going on, once you have generated those molecules, and this can be hundreds of different ones, it is actually just a matter of calculations to do this cross-grading and stuff like that. So Of course, you also have cases where you really do not know what you're doing, right? So this happens also quite a lot. So there's a lot of chemistry going on. Let's say that is basically 19th century or 18th century. That is still going on in the industry. We know that too. In that case, I'm not sure if this rational design thing that we are doing here, attempting to do, will help you, to be honest. Maybe then you just need AI, but if you do AI, you still need descriptors, and you need lots and lots of data. So if you have no knowledge of your chemistry whatsoever, then it becomes impossible. Now, for the case of the proteins and in the milk, that is very interesting. So these proteins that are there in these, and there are many different ones. Have these, I forget for the moment how they're all called, but anyway, these are known. At least the one-dimensional structure is known of many of these proteins, if not all of them. And so with this trick that I just said of the AlphaFold, feeding that into Culgi, we suddenly have the capability of providing, based on only the DNA sequence of these proteins, a possibility of saying something rationally about the behavior of those proteins, which is, I think, fantastic.
Okay, thank you. Next question, how large of a molecule can be coarse-grained by the automated mapping and parameterization procedure? For example, can it do an antibody?
Yes, without doubt, because we have already done that many times. Also, this is a bit of a secret, so maybe I should not be selling that, but if you do the coarse graining based out of, as I said, for this multiple sclerosis protein, of course we can also do it for an antibody. And the person who is interested in that, please contact Siemens, because we have a great demo on that.
Okay.
Also, I must say another one, which is also very interesting. I will go ahead. Is the vaccination. So we all know about, everyone knows about corona proteins, right? But there are many more vaccines being developed than only for COVID. And in many cases, those vaccines are based on the protein that sits on the outside of the virus. Now, it is very easy, relatively easy to get the sequence of those proteins by DNA or RNA, what type of viruses that you have. But then, right? So if you then want to make a formulation based out of that, that you want to, for your immunity, that you want to trigger that response, you need to, first of all, isolate, put maybe the DNA into a plasmid or something, and then generate your shell protein. But then, many of those proteins, the same as with corona, are maybe hydrophilic on one side, but extremely hydrophobic on the outside. That's why they sit on the outside of viruses. So when you do that, you hit immediately the problem that many of those proteins that you want to formulate for triggering an immune response are actually aggregating in your solution. This is the major problem in making new vaccination. So again here, and as we speak, this is something that we are working on right now, is to take that idea from taking the coarse grain structure via the AlphaFold and then going all the way to the aggregation, something that we can do with vaccines exactly the same.
Okay, time for just a couple more questions. Next up, is Culgi able to simulate protein molecule interaction with packaging material surfaces, including protein aggregation simulation?
Yes, we also have an example of that. Unfortunately, I do not have it in my presentation today, but do we have examples of, for example, of proteins aggregating with a surface that was tetted with, I believe, polymers to some extent, and then the question was if this protein would sit on that surface, yes or no. Okay. So we have done that, yeah.
Okay. Is it possible to simulate segmental relaxation for semi-IPN system?
Semi-IPN system. I really need more information on that.
Okay.
It does not...
We'll skip that one. Okay. That's all it says. Okay, here's one. One challenge while developing a formulated product, which includes developing a new ingredient, parens a new polymer, is the iterative process of customer feedback. As an example, one property of the polymer that we track is the rheology profile For example, modulus of the polymer. Is it possible to model the modulus of the polymer and also predict the property of the formulation, for example, flowability?
Yes, also very good. So, by the way, when I was listening to you, I also realized that that IPN could mean interpenetrating network, like you have in a gel. Could be.
Aha.
Yeah, could be. I don't know. But anyway, network calculation we have done many times too. So so going back to what you want to include in your screening. So I have shown that by this coarse graining trick, and then followed up with the rheology, we can include, or we can calculate, a viscoelastic property in a very early stage discovery in a relatively short amount of time suitable for screening. Now the question is very valid. So if I have other properties that I want to include in my early stage screening, and this can be many things. This can be something like, again, this simple thing like log P or something. So a partition coefficient, that's much easier. So if you want to go to the final polymer product, and if you have a good idea how to calculate the modulus of that, and we have done that too, but on a coarse grain level, not on a molecular level because that takes too much time, but on a coarse grain level, that's possible. It will maybe not exact, but for screening purposes, it will be more than good enough. In that case, you would need to, in your, let's say, meta experimental design of your screening, you need to run your Culgi calculation not only for measuring the, your viscoelastic response, but also measuring what would the final product performance would be. And then it is up to you to decide on how you want to weigh those two. Maybe you think processing is more important. Maybe the modulus is more important than processing. A lot of process engineers will not agree with you because they think, I cannot make it, right? You can make fantastic polymers that have in the laboratory. You can design fantastic polymers like these very stiff ones, that can do marvelous stuff. But you simply cannot process them. So the weighing of the two is up to you.
Okay. That is all the time we have today. Thank you again, Dr. Frye, for your fascinating presentation. And thank you to our participants for being such a great audience. Thank you to On24 for technology and production services and Siemens Digital Industries Software for the sponsorship that made this interactive webcast possible. Be sure to check CNEN or CNEN Online for information on upcoming webinars. And for CNEN webinars, I'm Catherine Dold. Goodbye.
Okay, thanks you all. Goodbye.